much. It's really a pleasure and an honor for me to be here, and I really mean it. I've been delighted by both my scientific experience in India and also my visit, my encounter with this very different world. You see, I'm from South America, and I've always wondered what it could be to be at the moment of the encounter of the different cultures that make our own culture. And now I can see what it means to be in the face of a whole universe to discover, and I find it really very interesting.
Where are you from, South America?
I am from Venezuela, so the north of South America. Okay. All right. And this is University of Geneva. So I don't know if, well, some of you for sure were at ISM. This is actually based on some slides that Julian Sonner prepared, but I will be introducing some other material so that you actually get to see something new. So this is work I've done with my supervisor, Julian Sonner, but also with Pranjal Najek, okay, so son of TIFR. I think you will recognize the mark of TIFR, the pedigree, in some of these results, all right? So as I said, well, some of the slides are based on set prepared by Julian, the nice ones, okay? Those, so we recognize the lion by his claw. If you see one that seems rather defective, so that will be by me, okay? So when I first wrote a title for this talk, I wrote actually ETH in the SYK model. But then I figured that maybe some people in the audience may not be familiar with ETH SYK. Unfortunately, the only change I could do, you know, to make justice to, or to make it more clear for people not familiar with this was the title. So if some things seem, you know, like very far from what you usually do, you should feel free to ask me the details of it. But actually, it will be a rather standard presentation of a Hamiltonian, and you know, computing certain dynamical quantities of a Hamiltonian and studying thermalization behavior. So this is actually basic notions that we are all familiar with. Okay, so let's start with ETH, a notion or the hypothesis. Okay, the eigenstate thermalization hypothesis. So it provides an explanation as to how closed unitary quantum systems can exhibit thermal behavior in pure states. We will see specifically what it means for matrix elements of observables in eigenstates. Okay, and we examine a specific model. Okay, some Hamiltonian, the SYK model, as well as its infrared limit as described at an effective action that we will see is of the form of a Schwarzian action. And we show that, okay, so this is the upshot, as expected from evidence found using exact diagonalization, the model satisfies ETH, okay? In the Schwarzian limit, so this infrared, actually part of the infrared description of this model, we study a specific class of the states created by heavy operators, and we find that they only show a weak form of ETH, and we will see what I mean by weak form, and we will see why it is interesting that you only have this weak form in this limit as opposed to the full ETH, okay? But why do we do this? Okay, for those familiar with the ADS-CFT correspondence, and also if you're familiar with everything that has been going on lately in our community, one of the reasons, or perhaps the main reason why people study the SYK model, okay, not ETH, but the SYK model, is that it may have a gravity dual, okay, and in the gravity dual, if there is a black hole, okay, you take this as a synonym of, you know, thermal states, and therefore you can ask questions about thermalization. So actually, the main question of we have in the back of our minds when treating this model is the problem of thermalization and its relation to black hole formation and evaporation. Okay, but there are also other reasons. So thermalization of closed quantum systems is a very important and general question, okay? And actually, this model is one of the few that provides an arena where you can attempt to test this analytically. There is evidence of ETH. I haven't introduced actually ETH, but just take it for granted now, that ETH is satisfied in many different spin chain models, but this is evidence using, you know, numerical techniques. Now, analytically, you can also take some other models that are simple enough, and in particular, CFT2 is another example where these things may at least be attempted, okay? And well, this is also related, as we will see, to time evolution and spread of entanglement, and in general, the question of black holes, as I mentioned before. Okay, so but now let us see what this ETH is. And in particular, having in the back of our minds, although I won't be talking too much about it, whether there is a geometry of eigenstates. Okay, but this is in the context of the ADSC duality. So this is a highly non-trivial statement. We will see why, but there's evidence that there may be such a thing, at least for this model. Okay, a geometry of an eigenstate. So let us look at our framework. So we take a step back and we ask the question as to why closed quantum systems thermalize. So eigenstate thermalization gives an answer to this. So this is a proposal that dates back to the 90s, okay, by people like Sachdev-Ye-Kitaev and David Deutsch, and has been studied in the condensed matter community for the last 20 years or more. And what it says is that if you have matrix elements, so this is some simple observable, O, say simple in the sense of a non-extensive. If you think as a spin chain, then you would like to take observables that involve only a few sites. Okay, so suppose you take here the number operator at a given site, or say the hopping operator between two neighboring sites. Okay, you study then matrix elements. So this denotes here matrix elements when you compute O in the basis of eigenstates of the Hamiltonian. Okay, so this denotes an eigenstate with energy Em, and this an eigenstate with energy En. Okay, and so these people show that if these matrix elements have this form, then you can see that actually the system thermalizes in the sense that this expectation value here actually coincides with the thermal expectation value.
Should this be true for every eigenstate or for generic eigenstates?
So first of all, there is a question of should it be true for any observable? Okay, the answer is obviously no. Okay, you can easily build something that does not thermalize, neither here or any other state you want to evaluate it in. In particular, you can compute things that are constants, that are conserved quantities. Okay. Now, should it be true for, in general, actually, we would be thinking here more of high energy eigenstates. However, okay, it depends on the system. It depends on the Hamiltonian. It may as well be that the ground state contains, and it also depends on what question you're asking when you refer to thermalization. What thermalizes? This quantity here, or is there a combination, some higher correlation function? There are quantities for which already the ground state may contain the information about the time dynamics that you want to compare with when asking a question of thermalization. So we will see some examples, and we will see in which sort of quantities already even low energy eigenstate, at least for the Hamiltonian, we're interested in those already.
Well, let's say above a certain energy. Is the conjecture that this is true above a certain energy for every eigenstate?
The conjecture is that this is for a generic eigenstate.
No, so is it for generic or for every?
For every, in the sense that you will have this suppression here. So it will, of course, depend. So let me now tell you a few words about what this is.
One eigenstate for which it's not true, that falsifies the ETH conjecture for that system. And I just want to understand. It's not good enough for you that it's true for all except a few.
Yes. No, it should be true for all of them. In particular because, well, you will say, okay, but I can easily find one in which this will deviate a lot from this is a microcanonical expectation value. Yeah. So the statement could be that, okay, it may be true, but you also have this suppression here, and for that one, the value of the entropy at that specific, this is the entropy. Okay, so let me actually say what these terms are here. So the conjecture is that in the diagonal part, okay, you have some smooth function of the energy E. So this is the average energy. This would be En plus En by 2. And that you have, for the off diagonal, something that is exponentially suppressed with the entropy. Okay? The entropy evaluated at that average energy. This could be some smooth function of E and the energy difference. And this is some random variable drawn from a Gaussian distribution of unit variance and zero mean. Okay? No, so, okay, so the statement about thermalization could be that this really approaches this, okay? So if the energy is large, usually this thing will be really, suppressed a lot. And so this won't compete with this. It may happen that for low energies, okay, this term is comparable to this one. And so when you take this average, it doesn't actually coincide with the microcanonical or the thermal average. So there will be contributions from the off diagonal that may, spoil your.
Doing analytic computation, you will anyway be able to separate between these two terms, right?
Yes. Yes.
So you're talking about a problem if you are doing it, using numerics, when these two terms will come.
We will see in both cases, analytics and numerics, and we will see how.
Even analytically, you'll get an answer for M O N. How do you separate these two? I mean, there has to be parametric separation for you to be able to separate.
Yes. Okay. So this is the ETH, all right? And so the statement is that individual eigenstates are thermal in this sense, in the sense that it approaches this value, the diagonal one, and there are some corrections, but they're very small compared to the thermal one. And time evolution reveals this. So is this the case in holography? Okay. So typically, to answer this question, okay, analytically, many body spectrums are out of reach. Fortunately, you have systems for which this is actually something you may try to do, as I said before, and we will be doing it in a specific model. So let me introduce that model. Okay. So this is a random quench disorder model with an all-to-all coupling. So these couplings are these J's here, okay, and they are drawn from a Gaussian random distribution, okay, with these properties here, okay. Here I'm using the complex version of these. This can also be written in terms of just some Majoranas, okay, sides. But here I'm writing the complex because in the numerics it will be easier, okay, for reasons that are not too important at the moment. So you have these all-to-all, okay, couplings, and it's a given Hamiltonian. So take it just as a Hamiltonian. It is interesting for a number of reasons. Okay, let me just cite a few. Okay, one of them is that if you compute a quantity that is also computed in the gravity dual, I know most of you are actually familiar with it, but let me say nonetheless. This quantity known as the Lyapunov exponent as defined by, a 4-point function, a given 4-point function. If you compute that in black holes, okay, then you obtain a value that is actually the maximal possible value this can attain. And if you compute it here for this simple Hamiltonian, at least in a certain limit, okay, you will also find that saturation. And so this reveals that possibly a connection between the two. And there are other reasons that lead you to think that. So just to explain why you could look at this, other than the reason that I cited before, this is an arena to explore analytically ETH. So now let's look at what we obtain for this model, okay? This is the numerics, okay? This is a part of the numerics. We find numerically that this is indeed satisfied. In which sense? Well, this is actually the matrix, okay? This is the matrix OMN, okay? What you're looking here are the numerical values of the entries of the matrix, and you have some code color here that illustrates the magnitude of every entry. And as you can see, there is dominance of the diagonal ones. The rest is basically some noise, but the values of the rest are basically 0 or something very close to 0. In any case, very small compared to the diagonal ones. Okay.
This is for one particular realization of the random J's?
That's a very good question. Okay. So this matrix here could look very much the same if you take 1 or 100 or 1,000. Okay, this thing. However, this other plot, so let me tell you what this other plot is, wouldn't be the same if you take only one copy of your Hamiltonian or many. Okay, let me say a few words about the copies. Okay, actually, what is supposed to have a dual, a gravity dual, is some disordered average of it. So you should think of it as taking many realizations of this Hamiltonian and then averaging over those different realizations. Now, when I speak of a single eigenstate, am I talking about a single eigenstate in one particular copy of your Hamiltonian or not? If I take many realizations and I average over all of the realizations, it is impossible that, since it's a random coupling, it is impossible that in all these realizations you will have exactly the same spectrum. And in particular, it may as well be that an eigenstate with energy E0 in a copy is simply not something in your spectrum in another copy. So when I speak of a single eigenstate, but in the case of many copies, I'm actually speaking of a window of energy. I select some energy E0 and I said, in all the different realizations, when thinking of a single eigenstate, I will be thinking of eigenstates that lie within a very narrow window around that E0, so that I make sure all of them have some eigenstate that lies in that window. Okay? But why is it an important question? Because, well, when I plot this, so what am I plotting here? Just the diagonal values against the energy. So basically, I'm trying to plot this function O of E. So this is, the conjecture is that if it's a smooth function here, okay, then you prove thermalization for this. And this is indeed a smooth function. But this is a smooth function after having taken many realizations and averaging over them. If you take a single realization, you will have very scattered plot here, many points everywhere, okay? And you cannot read a smooth function from that. So here is one aspect in which only the average version of SYK will lead to a smooth function here, okay?
So when you say you average over many realizations, do you average like many Hamiltonians first, or do you average the expectation values in the end?
I average the expectation value, yeah. Because if you average only the Hamiltonian, okay, you won't be doing much. I mean, I give you a matrix which has some random entries, okay? Then I give you a second one, and you average the two, but then what you will be obtaining is just another matrix with some random thing. I mean, averaging over the Hamiltonian itself would not lead to, and then what my point is that you could have only one Hamiltonian in the end on which evaluate this. So you should think of it as computing OMN for every copy and then averaging over it, okay?
So is there energy eigenstate nearby, suppose from a given reference state, if you vary randomly the thing, is there always a possibility that for all possible realization of object you will have an energy eigenstate near the original reference eigenstate?
Yeah, because, well, I didn't plot the spectrum here, okay? But it's on very dense spectrum around certain values. So if you pick that value of the energy where you have very dense, it's very likely that you will have in all realizations an eigenstate lying within the window. And it doesn't matter if some of them do not have it, because you will take many, okay? So this could be for 1,000, you see here? It's very small, so maybe you cannot read it, but this is actually the diagonal expectation values for 1,000 realizations, okay? And here,
over 1,000.
average
over 1,000.
over 1,000 realizations.
And the left-hand side has been computed at a single realization?
Yes.
Because I don't even know what it means to say MN.
No, one, yes. So this is for a single, but even for a single, you can see this is certainly suppressed, the off-diagonal ones. The question is not only that it has to be suppressed, it's also important that this be a smooth function. Actually, when you prove that this leads to thermalization, to the thermal expectation value, it's very important that it's a smooth function, okay? And also this one here, okay? So let us now, well, we're checking every statement here.
Sorry, E by J was
Yeah.
energy by J, but there's no N in your problem?
So this is, so here you have three different curves, okay? And actually, each of those are for, so one of them is for n equals 10, the other n equals 12, n equals 14. This means that your Hilbert space dimension is n to the 10, 12, 14.
And as you increase N, does the thermalization improve?
Very much so. And we will see in other
And do you expect that as
And
N goes to infinity, it will thermalize even for a single copy?
Exactly. So that's a very good point, okay? Indeed. Because this is indeed not a smooth function for a single realization, but also your n is very low, okay? The question, natural question is, for very large n, maybe a single realization encodes already everything in it. So we will see about that.
So the fact that you're studying ETH and the Spike model saturates the chaos bound. So in a sense, it thermalizes as quickly as possible.
Yeah.
So does it show somewhere, like in this analysis, when you study like maybe the off-diagonal elements, do they show some characteristic behavior? The fact that it's not just an arbitrary system, which is thermalizing, but a system which can thermalize as quickly as possible.
That can thermalize very quickly. Yeah, that's something you can see.
So where do you see it here? Like
We will see. We will see in a sec. Okay. So far we're just checking these statements. Let us now check about the off-diagonal. They also should be. You should also have a smooth function here and so on. So let us check that. So to compute f, do the following. I said that Rmn is drawn for a unit variance distribution. So compute the variance of OMN. If you compute the variance of OMN, this term won't be there. RMN is supposed to be unit variance. Now, count the number of states that lie within the energy window you have, and you will be able to count the entropy, to obtain the entropy. Multiply by e to the s by 2, and then you would read f. Okay? So that's what we did over many realizations, and this is basically the function f. Here I'm plotting it against omega, the energy difference. It's a smooth function, and one can see it also as a function of e. It's a smooth function. And now let us notice something very peculiar here. Okay? You have a smooth function that is basically a constant, and then you have, this is a log-log plot, and suddenly you have, a very abrupt change in the behavior of the function. In the context of many-body localization, people like to call this, when computing actually this very f, okay, but people like to call this the tailless energy as the, referring to the energy where random matrix theory behavior, okay, breaks down. Why do I say random matrix theory behavior? Because actually one can check trivially that any RMT theory, RMT will satisfy ETH. So that ansatz for a given matrix drawn from some RMT is satisfied trivially. And trivially with an f that is basically a constant. But let us do the homework. Let us do the homework before the homework of checking what it would look like for a random matrix theory. Okay? But before that, there is one more thing to check. This RMN. Okay? This is actually also important. How do you check for this RMN? We already assumed that it will come from a unit variance distribution when we computed f, okay? Because that's how we read f. But other than that, we haven't really assumed the exact details of the distribution. So let us now compute RMN. To do that, now that you have your function f, multiply the off-diagonal elements of O, okay, against check the values of OM and the off-diagonals, but multiply first by the inverse of f, so that you get rid of this term, and multiply by e to the s by 2, so that you get rid of this, and now plot this histogram. Okay. This histogram shows that this is not a fit, I'm plotting two things here. I'm plotting what ETH tells you it should be, so the blue continuous line, okay? This is what ETH tells you it should be, and the rest is what it is. Okay, as you can see, it actually, I remind you that we have assumed unit variance, but nothing more than that. The details of the actual Gaussian distribution actually then are satisfied. Okay.
But ETH makes a prediction for this?
For RMN, yes.
What is the prediction?
So other than, so first of all, that is a Gaussian, okay? Because you can have unit variance distributions, but it need not be Gaussian. So most importantly, that it's Gaussian, and it is indeed Gaussian.
And
with zero mean.
With
and
zero
we haven't
actually unit, not variance 1, not variance 2.
Yeah, 1. Okay, so here you are. But
variance 1 and 2 can be absorbed in it.
Yeah, sure. I mean, up to yeah. Okay. All right. So checked. That we checked. Is it just RMT? Are we doing some trivial? Are we doing some trivial check for something that in the end is just some easy random matrix theory? One can think that, because after all, the Hamiltonian, you see, you have these couplings, okay, drawn from some Gaussian distribution, and you may as well think, okay, maybe this in the end just reduces to some RMT. But I already hinted at the idea that it is not, because when we plotted the function f, I already told you for some RMT it should be constant. And I'm showing it here from some numerics. So you do your homework and you check actually using this same code, you check for some RMT, in this case some GUE, okay, average over 1,000 realizations, so that we compare the same thing. And this is what the function f looks like, you see? Look at the scatter points. So this function, this continuous curve here is actually taken after averaging over, this is the running average, okay? So otherwise you could have these scattered points here, but when you compute the running average, you see the smooth function, just a constant. So SYK is not just RMT. There are more non-trivial things lying there. And actually, if you think about it, it shouldn't be just RMT. After all, your Hamiltonian that has these couplings, but also this creation annihilation operation.
What is GUE?
Gaussian unitary ensemble. So there is a classification of what from which distribution you could be drawing your random matrix, and this is just one. But we have checked for many of them.
Can you go back one second?
here.
You say the blue line is at the outside envelope of blue line is a prediction, right?
Yeah.
So, but then the graph fills out everything inside, and I didn't understand. Then what is the thing that we're checking?
This is probability that this value here lies at some, it's say -2, then this is a probability that it's -2. This is a probability that it's 0. As you can see, it's mostly 0 because, well, it's supposed to be.
I think Ronald was asking, is the blue shading just artistic convenience? Or is it
No, this is the actual. This is what you're seeing in the. You see, these are actually. This is a histogram, so these are actually vertical lines. So this is a probability that the value lies
Block
there.
one on top of the other?
Yeah. Yeah. So no. What this is to see that it's actually satisfied. It's not just feeling. No. I mean, it fits so well that it looks like. Okay. So let us move on. But so not just RMTs, non-trivial statements. Also, now let us look at some more, some quantity that contains a little bit more information about dynamics. Say this 2-point function. Okay. So in all these examples, we're looking at the number operator at a given site. Okay. Let us compute it, evaluate it in eigenstates, in the thermal state, but also in another state. Well, Gautam is not here, but this was actually a slide for him. And in a state that is a Maldacena-Curculus state. So this is some state that in the context of holography plays an important role. A state that is supposed to model thermal behavior very well, okay? A pure state that is supposed to model thermal behavior. But what we are showing here that even for a single eigenstate, okay, many realizations, but a single eigenstate, this quantity actually, approaches what the thermal expectation is. And at least for early times, it seems like there is no distinction. And then for very late times, it seems like there is a difference. But as you increase n, that difference is reduced. Okay? That difference is reduced.
Sorry, so I didn't understand. Which were what plots were?
Yeah, so here we're plotting this 2-point function, okay, against the time. And this one of them, so let us see. So this is Gn, so this one, this blue here is for eigenstates. Okay, so this is important. How do you compare, since you should evaluate it at a given temperature, at least the thermal one, okay? The thermal one you should evaluate at a given temperature. This other special state has a way to map the temperature to some parameter, so let us not focus so much on that. But in the eigenstate, how do you say, okay, I'm computing this 2-point function at temperature beta equals something? How do you say?
You take the energy at gunpoint by thermodynamics.
Exactly. So what you're doing is basically, well, you take 1 by C, and then you simply trace of e to the minus beta h times h. This is the expectation, the thermal expectation value of the Hamiltonian, therefore the energy, and then you can do a map between this beta and E. So this is for finite n, and so the ensemble equivalence may not be, for a very relatively small Hilbert space dimension, may not be valid to all extents, but at least it's a way to get a map and then be able to compare. So actually, we are computing this 2-point function, an eigenstate that has energy E that could correspond to the value of beta in this that you compare it with for the thermal case. So the statement is basically that these things seem to coincide, and that for many realizations they seem to be so.
What is n in this?
N? N is just to label the fact that you're computing OO in some eigenstate n.
No, I meant
Oh, you mean capital N? Yes, capital N here is 6. So this is 2 to the 6, not very big indeed.
Why do you see? Why do all behaviors have this universal early time period? I can't even see, but are all?
Yeah, they basically are on top of each other here. Yeah.
Is that just the back? Why are they all so good at early times but worse at late times?
Well, I don't think I know the physical reason behind that. I mean that the eigenstate would encode only early times and not late times. It's not something you can really see from. You would expect that it encodes everything, but I suppose the interaction. I mean, when you have a more complex dynamical quantity, something seems to play a role that I don't understand completely as to the late time behavior. But something that is certainly playing a role here is a finite n, okay? That at late times it doesn't. So the question would be more why for a smaller n the eigenstate is encoding, I suppose just the dimension of the Hilbert space should be something that hints at this.
Is dark blue thermal? Which one is the Maldacena-Kurkulu and which one?
Maldacena-Kurkulu is the light, is the purple.
Purple? Dark purple. Okay, and the light blue is thermal?
And the light blue is thermal, yes. So even Maldacena-Kurkulu doesn't quite coincide here with the thermal, but also again for larger n these things improve.
Okay, and there's an analytic prediction for the thermal two-point function.
Yes, if you
in the middle of that.
Yes, exactly. Okay. Okay. So, but
so it's interesting where the strong coupling expansion takes over. That's where the deviations are mentioned.
Yeah. Yes. So let us look now at another non-trivial quantity that encodes a lot of dynamics. So I was saying before that SYK is interesting because you can define some number here. So that is a number this is the number I was referring to. If you compute this correlation function, okay, so it's called the out-of-time order 4-point function. It has a behavior schematically of this form, and here we'll be setting some exponent. And this is the quantity that is saturated. This is the bound for this quantity, as found by Maldacena, Schenker, and Stanford. Okay, and for SYK it's satisfied. But let us do then our plots. Okay, why not look at our plots for this and see whether also for this the more non-trivial quantity single eigenstates encode the dynamics. And here they are. Actually, this is more non-trivial, so n cannot be very large. Again, I think n is basically 6. Okay, so 2 to the 6, not very large. But you can already read something like the Lyapunov exponent. And at this level, if you increase n or decrease n, the numerical value that you would read from here we are basically reading lambda, doesn't change too much. So, and again, the curves coincide for early times. It's very thin, so it's hard to tell. But believe me, here there are two curves, one thermal, one eigenstates. And they coincide for early times, and then you have some deviation here. And well, it seems like you could conjecture that even for a single eigenstate, you can read something like a Lyapunov exponent, and the beta that will appear here is just the beta you could draw from here. But single realization. Okay, I said before there is a subtlety, and let me show you this plot here. This is another quantity. This is another quantity that has some dynamics. It's called the spectral form factor. Actually, it's defined like this. Okay, only information about the Hamiltonian. You see, no operator here, no observable O. Only partition function. So your Hamiltonian encodes this, and let us see how a single realization encodes, or to what extent a single realization, a single eigenstate of a single realization encodes the dynamics after taking many. And here you have a single realization is a lighter blue, okay? 10 realizations, it gets better. 1,000, well, basically some continuous line here. But look at this. Early time, a single realization basically encodes everything that the rest has. Okay. In particular, if you wanted to read, say, this, okay, the slope here, then a single realization could be enough. And again, if you increase n, big N, then this light blue thing will actually approach the continuous one. So this leads to the question, okay, does a single eigenstate actually at large n encode all the information about the dynamics, at least for these quantities? Okay, this is for n14. This is a simpler quantity, so you can go to higher n. So let us do some analytics.
Sorry,
Yes.
So the single eigenstate was the light blue?
The light blue. So it coincides here, they overlap, and then it starts to deviate. Actually, you see, there is non-trivial information in at which time this happens, and also for the ramp. So it seems like for the ramp, you couldn't be able, for finite n, to say a lot about what happens here.
But even at infinite n, wouldn't you expect it to oscillate a lot for a single realization?
Well, so my intuition, at least from looking at the plots and this, would be that it would oscillate a lot, but you could read at least, if you take the running average of it, the running average meaning now you average, you know, you drew up a point by averaging what is in this windows, if you divide it in windows and then you draw that line, that average should give you a smooth line that you would obtain for many realizations.
Right. But the information about the particular scatter will change from eigenstate to eigenstate, right?
Yes. Yes.
Even at large n.
Even at large n. Okay, so let us look at large n, because that's where also the analytics can be done. Okay, so let us do some analytics. The question is very easy, the question we are asking. Okay, do these quantities satisfy ETH? I mean, in particular, let us first ask the question, does the SYK model at large n satisfy ETH, but can we prove it analytically? Okay, so how do we do that? Well, at large n, there is a description, actually. First, because you have this disorder average, so we will not be looking at a single realization, in fact, in the sense that when you do a map, so this Hamiltonian, okay, so this model, if you wish, you can rewrite it in terms of some effective action after doing some disorder average. This could amount to taking many realizations and then averaging. So frankly, it's not like we're looking at a single realization and then looking at the large n. It's more like we're actually looking still at an average over realizations, so this disorder average, but then looking at a large n and seeing what happens. So just take for granted that you can write an effective action, okay, for this model. And here I've written the Majorana version of it. Before it was in terms of C dagger C, but it can be done also for the complex model. And the statement is that if you now go to the deep IR, so two things to keep in mind. We're taking large n, and also we're going to the deep IR. Okay? The statement is that deep IR is conformal and broken by some correction. And that correction is basically given by a Schwarzian action of this form. So, sorry, I didn't write here what this stands for, but it's some combination of derivatives of f's. Okay? And so let us be a bit more explicit about it. The statement is that in deep IR, you have a contribution that is conformal and something that breaks that conformal invariance. Okay? And the reparameterization invariance of this action here actually means that when you compute, say, a two-point function, you can see that this is what it gives. But this reparameterization implies that actually you can, without action cost, also go to a two-point function that gives given by this combination. Why do I say this? Well, because we will be interested in computing these sort of quantities, okay? So we will be interested in particular in a path integral computation in finding saddle solutions for f and then plugging them here.
So this is Euclidean, at the moment you're in Euclidean space?
Yes, I am, okay. So so you should think of this behavior as you have some conformal a two-point function, and it's broken by something that depends on this. So this is SCH, it stands for Schwarzian, which is the same as this notation. It's just a different notation. And so you have these corrections at the alcohol. So this is the combination of derivatives that comes in the Schwarz. Okay, so what do we find there? So you have two sectors basically, or if you wish, you can divide it into two sectors. You have a conformal sector. So this, look at this. So what we will be doing two things analytically. We will be looking at the conformal SYK, so only the CFT action, okay? And there you have a discrete tower of states. When you study the spectrum of this model, you will have a discrete towers of states of this form, okay? Some derivatives of the, the C's or the psi's in the Majorana case. And then you have the continuum given by the Schwarzian, and this is the full spectrum. And we will be asking the question, is ETH satisfied for observables of this form in the conformal? And what we will be finding it is. In what sense? In the sense that when you look at OMN, okay, they look as, you have some smooth function in the diagonal and then something exponentially suppressed in the off-diagonal.
So when you say discrete tower states, you mean discrete tower of operators?
Of operators, yes. In this case, operators, because when we, that's a good point, because of course, when I say we will be computing OMN, what I'm actually saying is that we will computing say, OK, OL, say OP, just no. And I will be then these are labels also for the dimensions of the operators. I will say K and P are very heavy, and so I can think of them as creating a high energy state. Okay, so if I say that K and P are much larger than L, I can then think of it as something of this form, where these are states created by these operators. Okay, and so this is as if I were looking at the matrix elements of OL, so the matrix elements K, KP. So we will see that, and I will be more explicit about it. But this is a question we will be asking in this case.
Is there such a thing as a state operator map?
Oh, well, that's actually a very good question. Okay. Well, in this case, we will be actually seeing there's another way of writing it in terms of 2D Liouville theory. But actually, this is a crucial question for the case we are looking at. I forgot to mention, in terms of the CFT, this would be a CFT in 0+1 dimensions. Okay. So the dual should lie in, ADS2, at least when you have conformal invariance, or some near ADS2 in the full case. And the question about the state operator correspondence is very important. So we are assuming basically just right now that it is possible. And in this case, is clear because you have a way of rewriting it in a 2D Liouville theory. But actually that point, so we will go back to it later as we go. So the result will be that it's satisfied. And now, in this case, what we will find is some sort of weak.
These are sort of like the analog single trace operators, right?
These are, yes.
Would
single.
you be interested in some of the ends, some of the energies of order n?
Okay, very good question again. We will take the very large limit for these things, but they won't be scaling with big N. So let's call them middle weight operator. Okay, they are not heavy in the sense that they are not scaling with big N, but they are much larger than this one. Okay.
So this is the situation in n equals 4 angles where you wouldn't expect.
Exactly. Exactly.
Easy
No. Okay. But let us see what we obtain, and then we'll see. Actually, there are many implications for you. So.
Even in 2D CFTs, the heavy states always scale as C, right? With thermalization.
Well, the heavy ones, when you study thermalization for those ones, then you obtain that.
Only only observe in those cases, right? Whatever proof of thermalization in 2D CFTs.
Those are, yeah.
You don't even have black holes in 2D CFTs for energies less than C, right?
Yeah, exactly. You have the threshold there. Okay, so good. And then there will be the other case where the Schwarzian mode dominates in the path integral, and so all you could be doing here is taking, computing via path integral expectation values for some operators, and then seeing whether this behaves thermally. Okay, let us then be more explicit about it. Let's look at the conformal as well. Okay, and as I said before, what we will be basically computing is this 3-point function. Okay. This 3-point function, and we will think of these two guys here as creating these states, okay? And now you want to study this quantity, and this quantity should behave like what ETH predicts, or, well, that's what you want to prove if ETH is satisfied, that these quantities. Now, a part of the job was done already by Gross and Rosenhaus because they computed basically all point functions of this form. However, those are expressions that, are highly non-trivial. It's very difficult to get to read, say, if there is a smooth function of the energy, because the expressions for these correlation functions are in terms of infinite sums and so on. But something that could probably give you some hope is the fact that we are taking this limit, and perhaps in that limit the expressions simplify and you are able to read this behavior. So again, this statement is you have the middle weight operator in the sense that these are much larger than K here, but do not scale with big N.
Where K is just some number.
Some order 1 number, yes. Okay. All right. So the expressions are really overwhelming, so it doesn't make sense to show all of it. But the statement is that when you take that limit, that very limit, then this 3-point function simplifies to something like this. And then you can find a form for the Kronecker delta, okay, some regularized form for it that is written in terms of some combination of gamma functions. And actually, when you use that form, you can read explicitly here is the Kronecker delta sitting, okay, multiplied by some complicated but the smooth function of the energy, and then you have the rest, and the rest, the off diagonal, are basically suppressed as they should be. Okay. Now here is something that I'm perhaps lying under the carpet. It's the fact that how do you read that RMN are drawn from some random. That's actually very hard to read in the sense that you are doing some averaging over the coupling in this computation. And so it's not clear how you could be able to read precisely, okay, this is the RMN as it is, but these are things that will be, in any case, contributions of order 1. Okay, this will be presumably some unit variance thing. So that's something that I personally don't understand completely at the moment, but the statement about at least the exponential suppression with the entropy and all that, that one can see.
If you did this for a free gas, if you computed the same quantity, similar quantity for free gas, what would you find?
I think you couldn't find the thermalization behavior.
Okay.
Yes. So there's something surprising, and I think is what Shiraz is trying to get at, and that's precisely that we have found that ETH is satisfied for a state created by these conformal primaries, but not scaling with. So they do not in a path integral computation. They couldn't enter in the leading terms whatsoever. So it's in a sense you should not expect them to back react enough as to have appear in the ETH form this way. However, this is what the computation seems to suggest. So as if you were finding fields massive enough to back react on the ADS2. So this is something that I don't understand completely, but is what the computation suggests. So just to make the statement, then it would be very natural to expect that if now that is scaled with big N, then ETH is satisfied. But that's a computation I haven't done explicitly, so that would be just a guess. But I think.
What was the question about free gas? I didn't understand.
Well, in the sense that, as I was trying to say, they are not scaling with big N, right? And you, from the dual point of view, you could not expect them to back react. And so why would you see? It's as if you had a free theory, and in fact, the complex SYK has been shown to be, related to some generalized free field theory by Gross and Rosen.
Yeah, let's look at it in the context of N equals 4, which I'm more familiar with this. We know that at energies that don't scale with N, the dual description is basically a gas of gravity.
Mm-hmm.
The interaction strength is 1 over A.
Mm-hmm.
So if you're working in a, to first approximation, it's a free gas. And if you did a calculation there like this, sounds like it should be easy to do from the gravity side. And shouldn't give anything very non-trivial. Unless free theories have more of a surprise.
Yeah, then
So
we
at least
thought.
in N equals 4 angles, I need to put my
But why is this question relevant to the point?
because that's what he's doing.
Yeah.
Right? He's looking at a state at energies that are large compared to 1, but small compared to N. So that's like a highly excited gas of gravitons in ADS.
Yes.
But it's a free gas.
Yes.
Somehow the difference must be the Schwarzian.
Okay, so let's go there.
Yeah.
Okay. So the conclusion could be that at least the form of these OMNs, they have what the ETH is that what ETH predicts. Okay. Now let us compute heavy-like correlations from the Schwarzian action. Okay. Now we will be looking at a slightly different computation. We will be so the statement is that here. You see, in the computation of the Lyapunov exponent that I said is actually saturated by this model, actually you can see that already the largest contribution for that 4-point function comes from this soft mode physics, so the Schwarzian part. Okay, so in a path integral computation, at least if you take the saddle approximation, this is enough to compute.
So, could I be sure? There's no time in your calculation, right? It's just matrix element.
In this other one, yes.
Yes. And can I understand better how you're creating the state? You're creating the state by acting with the operator, but at a given time or at a late, early time. Can you say exactly what you're getting?
Yes. So it's actually, I think it's some arbitrary time because well, I can show you in detail with my notes how you create it from the point of view of the 2D Liouville. Okay, how they act, but they should not be thought as, you know, computing it at a different time will not make a difference in the form that they have. Okay, so you should think of them as computed at some arbitrary time but fixed. Okay, and then this is the result.
Will you just say let's say in the model, what
Yeah.
exactly are you computing, if you don't mind?
Well, so what Russ and Rosenhaus are computing are a ladder. They're computing using the summing up all the ladder diagrams, and so this is a computation that I think is
In
general
Euclidean space?
in Euclidean. Yes.
So tau 1, tau 2, tau 3,
Yes.
that 3-point function in Euclid.
Yes.
Okay. And you say the time differences don't matter.
No. Yeah. But of course, in our case, so and it will be more clear in this picture, you could be usually, well, also from conformal invariance, interested in sending the heavy ones, say one sitting at 0, one sitting at infinity, and then this one sitting at some time
So
tau.
this is what I was trying to understand. Your calculation is purely Euclidean, right? At a given temperature.
Yes.
So when you say go to infinity and so on, you have to continue to Lorentz.
You would have to continue
You're
to
not
learn.
doing it.
No. That if you do it, then that would be the natural quantity to look at, right? One sitting at 0, then one at infinity, and you look at it. But here, this is a general statement for the expression you obtain for the correlation function. Okay. And here it will be will be a very relevant question. So, what will we be computing here? Well, basically, we will be inserting some operators, okay, here, and evaluating the expectation value. And here, you see, as I showed before, okay, from reparameterization invariance of the theory, you can insert 2-point functions of this form here, but these 2-point functions have to be thought as two of the O's we had before. So these are some bilocal insertions. So you have a tau 1 and tau 2 as if you were inserting two of the O's we were looking at just now, one at tau 1, one at tau 2, but they would come with the same dimension, which I call here h and I call here n1. So that's why the quantity we're looking at is insertions of two of these, which amounts to insertion of 4 of the other O's, and with two of them, having the same dimension as here, and these two as here.
I just missed what you said.
Yes.
Well, what you before explaining?
Here.
Could you say what you're trying to explain?
Yeah. So let us see. We will be trying to compute. So the output is we will be computing this 4-point function.
You want to compute this at late times or arbitrary?
We want to compute this arbitrary times.
Okay.
We're going to compute this 4-point function. This is a 4-point function of these O operators. Okay?
Two of them are equal. They're equal in pairs.
Exactly. They come equal in pairs. Why? Because the way you insert them here are via this combination. Okay? In the action.
So sorry, you're saying that you're looking at that and you're looking now at the Schwarzian contribution to this 2-point
Exactly. Okay? So this is only in the Schwarzian mode. Okay? So we are looking at this 4-point function. And what do we want to do? Here the statement won't be exactly as here because, well, first of all, here we had a 3-point function. But what we will be interested in is just seeing if say, n1 is heavy, so if n1 is much larger than n2, whether what you would obtain, let me actually write down so that everything is clear. Where is the eraser? Here. What do we want to do? We want to compute this 4-point function, as I said before, but we want to do it such that if you compute the thermal 4-point function there, okay, so O n 1 at tau 1, O n 1 at tau 2, if you compute this thermal 4-point function, okay, now you consider n1 much larger than n2, say, okay, and then you send beta to infinity, okay. If the question is, does this look like the thermal 2-point function of these, the light ones, but with a beta, some effective temperature, okay, that depends on the dimension n1, okay? And so, for clarity, let me rename them as heavy and light.
And always Euclidean space?
Yes. This is the question. So we start with this 4-point function. We consider this. And why do we do this? Because when you send beta to infinity, okay, what you're doing is looking at, you know, the vacuum first, but then these heavy ones acting on the vacuum, okay? Those heavy ones acting on the vacuum create the state on which you're evaluating your correlation function. And the question is whether, okay, whether you obtain something that looks like the thermal 2-point function, but with an effective temperature that depends on the dimension of the heavy operations, okay? So it's not as in the case before, where we look at just the matrix elements and we say, okay, it looks like what the ETH tells you. No, here we're actually looking at something that has time, well, Euclidean time in it. And we are comparing it with the thermal answer. So that's what we will do. So this computation. And we will do it in particular in the, we'll take the saddle solution for F, okay?
Sorry, if you could go back one more, please. So now to go from the left-hand side to the right-hand side of that last equation,
Yes.
you've used how the Schwarzian couples to a particular operator.
Yes.
So those are those two factors.
Yes.
And that is the action to the Schwarzian.
Yes.
Fine, okay.
Yeah. So should I worry about the time or we can, okay. All right, so perfect. We are computing this, but and we are interested in finding, say, then now the saddle solution for F. So computing this in the saddle means you forget about everything here and you just evaluate the saddle solution for F in this combination, and there you are. You obtain an expression.
Now, the Schwarzian action has an overall n behind it, right?
Yes, so that's encoded in the G squared here.
Whereas because your n1s and n2s don't scale with n,
Yes.
they don't have an n.
Oh, so now we can again ask the question of the scaling of the dimension with n or no. Okay, so here it's arbitrary. So we haven't reduced to the case where it won't scale.
Okay.
Okay. Okay, so how do we find that saddle solution? Well, actually, well, you can attempt various things, right? You can just do saddle approximation here and then find the saddle equations and then solve for F. But actually, there is another differential equation that you can find for F. And that differential equation actually comes from the Ward identity. So one can prove that, you see, there is the law that in this CFT 0 plus 1, the Schwarzian plays the role of the stress tensor. And actually, the fact that under conformal transformation in CFT2, the stress tensor changes with a Schwarzian term suggests that. But actually, you can prove it. You can just prove that you have some identity where you have insertions of the Schwarzian with some of these operators, and that gives you something, some differential equation. So this is something that has been done in the literature and that we reproduce. And so what I was saying is that you have some differential equation that you can read from the Ward identities for this F, and you can prove that this equation is equivalent to the saddle equations that you could obtain directly from the action. But why do we do all this job? Well, because it turns out that solving this is easier than solving the other one. How come? Well, this is the Schwarzian derivative, which is a very non-trivial combination of derivative of F. But there is an auxiliary differential equation you can build that allows you to find solutions for F. So this is actually, say, technically the non-trivial statement. So let me be a bit more explicit about that. Okay. So
this is the business about boundary moving, right? The motion of the boundary. Malthus and collaborators keep talking about. It's the same equation.
I don't know. I wouldn't dare.
Well, you've inserted your sources far away.
Yeah.
So ignoring those insertions for a moment, here it's just free motion of the Schwarzian, right?
Yes.
Between. So that this is the equation of, if I think in terms of the bulk, it's how the cutoff of the ADS is varying.
That's right. That's right.
And that's the equation that people write down quite a lot, right? And
Yes.
Yes. Go ahead.
Yes. Okay, so now we want to keep in mind, we want to find f, the saddle solution for f.
So it's basically like classical mechanics for a single layer.
That's
With
right.
some potential.
That's right. And so there, let me just write it here as a mathematical statement. This statement here, that this differential equation, you see here, just to be a bit more explicit, this is the dimension of the heavy one. This is the relevant equation when one of them is much larger than the other. So only L1 is appearing here. So this is the heavy. This is the dimension of the heavy. Okay, you are inserting it in tau 1, tau 2. And then these are some constants that you should determine. Okay, and this whole combination here, let us call it T, okay, of tau. And the mathematical statement I want to make is that there's an auxiliary equation. This equation here is actually the monodromy equation or Hill's equation, okay? So there is in the math literature something called the Schwarzian and uniformization problem, where this equation appears a lot, this Hill's equation. But take it as a mathematical statement that solutions of this other equation, okay, with T given by this, can be found by solving this auxiliary equation here, okay? And I'll show you in a minute how they are related. And this is now a much simpler equation to solve, okay? So our T is basically, well, the insertions of our operators. And actually, it's very much like what you would have in the 2D CFT case, because usually you're writing as 1 by z or 1 by z squared, what's what appear here, but one can see that actually those are just ways of writing the delta and therefore derivative or integral of the
Even
delta.
before doing this fancy stuff, it was just an equation for one variable in one dimension, right? Differential.
For f, yes.
So it's clear that you could make sense of it.
Yeah. Okay, so I will just write the mathematical statement, how you could relate those two. So our original equation will be related to this auxiliary equation, and solutions for f, which is what we're looking at for. So solutions for our f will be simply given by, you take two independent solutions of that other equation, and they are given by this. Okay? Now this will of course come with some parameters that you need to determine to actually solve the differential equation. Okay? So those parameters will depend also on these constants that were appearing before here, okay? This kappa and these things. And of course, since this is a second order differential equation, you will have two such equations. So let me just write down what you obtain for f, okay, in the end. And this, of course, will be then the saddle. So let me write it like this. This will be what we will plug back into the previous equation as the saddle solution. And then it will depend on some complicated expressions, but in general, just some function of two parameters that we call omega tilde, okay? And omega. And then some combinations here. Okay, and some things that don't really matter, and something more here. The important part is that, first of all, you have these different ranges here for tau. Okay, tau 1, tau 2, and here you would have tau 2, tau. So this allows me to explain this figure here. What are we doing? The heavy ones, we're inserting minus beta by 2 here and beta by 2, so periodicity beta, okay? The heavy ones we're inserting here and here. The light one lets it insert at 0, okay? And the other light one at some point, tau 2, or let us call it actually x, okay? You insert somewhere else here. Remember, I erased it, but we want to send beta to infinity because otherwise you're just computing some thermal 4-point function, okay? So in these solutions here, okay, whatever you're obtaining here, of course, we need to determine omega tilde and omega. it will be very important that you send beta to infinity at some stage. Okay. So let me show. How do you before that? How do you determine omega tilde and omega? Well, our original solution, our original function f, has some periodicity, and this periodicity imposes something on these independent solutions for the auxiliary equation. Actually, that's called the trivial monodromy, meaning that actually, so that's how you determine omega and omega tilde, meaning that P1 at beta by 2, P2 at beta by 2 is, well, this will be some matrix. This is a monodromy matrix times P1 minus beta by 2, P2 minus beta by 2. And so periodicity of our F implies that this matrix here should be plus or minus the identity. And then you have enough conditions to solve for this.
Where is N1 and N2 in this?
So they are here. Sorry, the notation reflects the fact that we haven't put all things together, but actually this is the dimensions. They are sitting in this case they are sitting in tau, and they are also sitting.
As prefactor?
Yeah. So let me write that. Actually, let me go to what the monodromy triviality of the monodromy implies, and there we will see how they appear. Okay. So you impose this on the solutions you have, and then what you obtain is the following. You obtain that the tan of, so x is basically where you are inserting the other light one, okay, minus 4 omega, so I'm calling it now L heavy, so the dimension, 4 omega tilde square minus 4 omega square plus L heavy square by C square, and then second equation. Now already here one can think it's hopeless to solve these equations. These are transcendental equations for omega and omega tilde. And indeed they are very difficult to solve. One can first approach them numerically, okay? And the numerics suggest something that can be verified in the simpler case where actually these equations can be solved. So there is, I will show how these equations can be simplified. So to answer your question, here is how the dimension of the heavy appears. So these omega and omega tildes will be then functions of the dimension of the heavy one. The light one does not appear because in this expression, basically you say, well, the heavy one dominates, okay? And
so LH is roughly N1 by capital N?
Exactly. Okay. So numerics suggests the following. If you solve numerically for this, you plug into f, and then in the combination of derivatives of f and f that appear in this expression, okay, you obtain something that numerically, okay, coincides what would be the thermal expectation with something that has an effective temperature, okay, an effective temperature that depends on L in the sense that the higher the higher the dimension, okay, the greater the temperature. And so you say, okay, it's the heavy insertions are increasing the temperature, the effective temperature, but numerically it's not so easy to take this limit of beta going to infinity, so how can we approach this more analytically? So there is hope that you can actually solve these equations, and that's because first of all, there is actually, you can map this into this one if you look at these expressions, if you exchange omega with omega tilde and x with beta minus x, okay? If you exploit that, okay, you can simplify your equations by picking this configuration. This is a configuration where the two L's are separated by beta by 2, and therefore x minus beta by 2 is x. And so you exploit that, okay? And, okay, so these are mathematical statements about this equation. So it may not make sense to present it this way, but take it as a statement that exploiting that map you can do. In particular, in that map, for this configuration, omega and omega tilde are the same. And look how that simplifies enormously our equation. Because if omega and omega tilde are the same, what you have is basically an equation that is of this form. So you could have here again a transcendental equation, but one that you can solve in some particular limits, okay? And now you can ask the question how this is scaled with n, you see? That's this combination, let us call it L scaled. How does this depend on L scale going to 0, you know, or going to infinity, and so you can there. And precisely in those limits, you can solve this equation, okay? Perturbatively, of course. So what do you find? So those are just find omega, plug it, and what do you find? Well, the statement is you find a thermal, okay? You find a thermal function here, okay, with some effective temperature. But this effective temperature actually is proportional to the background temperature you want to send to 0. Okay? So it is an effective temperature that depends on the dimension of the heavy, in the sense that if you can increase the effective temperature, but if you send the background temperature to 0, your final result is just 0. So this is what we adopt the weak form of ETH, because you're not creating a black hole, you see. If there is a black hole sitting there, you increase the temperature, but you cannot create a black hole, at least.
What if the dimension of your operator is taken to be order n? Even so, you don't create a black hole?
No, because actually, if you send this to infinity, for example, okay, LSE to infinity, so what are you having here? So you're having basically a line. So actually, that's one of the limits we're looking at. So to solve this, we're looking at two limits. LSC going to 0. So they're heavy, but they do not scale with n. And so that could be, so minus infinity. So that would be a line something like this. Okay? And then you look at how it comes with the tan. Okay? So with the different, and you're looking at another one that you can solve when this is very heavy, and therefore your line would look like this, and you look at, you know, these intersections. So the more physical one, in the sense that you would expect to have a black hole there, could be this one. But even there, you have an effective temperature that has this behavior.
The surface state.
It is, yes. So what are these computations telling us? That well, what I just said, right?
No, I can't.
Yeah. So
Oh, maybe it's just that the state is king.
that the state was, sir?
You create a state here.
Yeah.
That's heavy because it's but then there's some thermal evolution that gives you an e to the power minus beta energy of that state. So you wait long enough, and that state basically decays away. Maybe that's what's hitting you. You know, if you tend, thermal evolution over a long time tends to project to the vacuum.
Yeah.
Maybe that's what you're saying.
Okay. Okay.
Because you took the beta to infinity fast.
Yeah. Why did you do in Lorentzian space? That would make more sense.
Yeah.
Then it won't do.
Yeah, so indeed, other things to do are naturally first how you define, strictly speaking, the thermodynamic limit, right? So you take n to infinity first and then beta to 0, or you take first beta to 0, then n to infinity. Sorry, to infinity, both to infinity, so the temperature to 0. And so there are all these matters that play a role in this computation. But this is the findings at least for that. Okay, so that's basically.
So you have to do this way because you know the answers for only the intuitive correlates.
But you can analytically.
No, you can. Yes, you can. So
there. So my suggestion is just do it in Lorentzian space. I don't think you'll see this funny decay. You see, because that is very physical. You're creating something. You're destroying it. What you're creating is heavy, so you must be following a black.
Well, so I.
You don't think?
No, well. So this is a computation I haven't personally done, okay? But there are some, so the thing is that I cannot remember exactly. So there is a paper by Ferlinde, Turiaci, Mertens, and Liam, where they do some computations of similar correlation functions. And they see that in one of these computations, you obtain something that where instead of a sinh, you get a sin, and so there is no thermal behavior. But I cannot now, since I don't remember exactly whether this was in the Lorentzian case and what was the order of the limit, actually tell or not whether this is known as to be not thermal. But I can check just now after we finish, and I can actually maybe clarify this issue.
Sure, but the kind of calculations that Maldacena and collaborators keep doing about the position of the boundary.
Yeah.
You've got this boundary that is moving around, and if the boundary stays forever, you've got a black hole. You know what I mean, right? Whereas if it goes and hits something, you've got no black hole. So, while I haven't followed the field in detail at all, but if you put enough energy, I presume it would make the boundary stay forever.
Yes.
How could it not?
Yeah, well, that's of course our expectation, original expectation, but at least this computation is telling us this, and of course there are other computations one can do, in particular with playing with the limits and the continuation, and there are some results already, but let me not advance. I can tell you in a minute.
And the Euclidean thing helped you because you could solve these equations.
No, but in the end, all they're doing is looking at the Schwarzian. In the second part, the last part of your talk, you're only looking at the Schwarzian.
Only the Schwarzian, yes. So
Schwarzian
you can do any. Yeah. Okay, so just to close, so we've seen that first of all, SYK is an arena to ask these questions about ETH. Okay. That some computations suggest that eigenstates could be thermal, but terms and conditions apply, as we have seen, and that correlations in the individual eigenstates are exponentially close to thermal ones with entropic suppression, and that we saw. Well, so thank you very much.
Questions?
So there's nothing known when a black hole forms, like a CFT2. I mean, it scales as C. I mean, but C is here don't scale like N or they scale as something. I mean, now if we take L by N, it may not work.
So there is a sense in which you may have a residual temp. When you send T to 0, okay, the background temperature to 0, there is a sense in which you may have a solution with some residual effective temperature. And how do you see that? Well, in this plot that I was drawing here, there are several solutions actually. You see? There are all these solutions. So there is a label for this, let's call it N, okay, depending on where you're sitting here. And if you don't pick the first one, but say the second one, then you will have some finite term here, okay, some residual temperature here. But how do you see whether these are physical solutions or not? Well, if you send L as scale to 0, there shouldn't be any effective temperature. Because, and so it so happens that when you send LS to 0, this residual temperature could be still there, and that's how you select only one of all the solutions as a physical solution, at least something that has, the
I think Orna was asking the large N thermodynamics that Maldacena and Stanford and other people found originally survives down to some temperature.
yeah.
And he wants to know what is the minimum temperature down to which it survives. And presumably that's 1 over 8.
Yeah.
I think it's very small. We say it's more like Poincare patch. It's like ADS5 and Poincare patch. Right? Any small enough, any temperature, no matter how small it is, I think it's like that.
But then light operators can also create it.
Yeah, it will, but now it's like, do you trust a black brain in ADS if its energy density is you can't really in gravity you can't distinguish it from zero. Interesting, but I had a related question to
Mm-hmm.
which is this. I wanted to understand what the implications of the Schwarzian are in Lorentzian
Mm-hmm.
for the spectrum. So suppose you take the Schwarzian and you quantize it.
Mm-hmm.
You get some spectrum. But of course it's a very small spectrum. Because you just have one mode and you're quantizing one mode, so you get order 1 states.
Yes.
The full theory, as you alluded to many times, has a continuum
Yeah.
of order n squared. Okay. What is the role? The Schwarzian seems to play a very important role in certain things.
Certain things. Yes.
But is there some sense in which the part of, firstly, is there a sense in which quantizing the Schwarzian gives you something meaningful? And if so, what meaningful quantity about the actual theory? Should one associate a Hilbert space with Schwarzian? Should one, is it part of the actual Hilbert space? What part? Is there something special about that?
So, you see, one of the reasons why you actually make physical sense of the full thing is, at least in the deep IR, the approximate conformal invariance that you have. And that's why you think of, well, at least I believe that's why you could think that the theory you are working with, will share features that other physical theories have. Now, when you single out the Schwarzian, as you were saying, if you want to compute the OTOC, this will be the leading contribution. But this need not mean that for any other quantity you compute, the information is encoded in the Schwarzian. If this were true, this computation we did is true for Lorentzian or any other combination of limits you take, what this is telling us is that whereas the Schwarzian contains all the information about chaos, about the Lyapunov exponent, it doesn't about these other dynamical quantities.
Sorry, I didn't understand how you concluded that. Which dynamical quantity does it?
For example, the fact that ETH is satisfied for the conformal sector, but not Schwarzian alone does not.
The last part of your talk seems to you to indicate that?
It seems to indicate that the Schwarzian could not contain all of the information for the ETH.
Or you've done the wrong calculation.
Or this is not a calculation that good
I
as.
think you've not done the right calculation. You just should move to Lorentzian.
No, but okay. So that's why I don't want to advance it now. But let me say, it's a computation we have either done explicitly or existing in the literature. I just trying to remember in which sense that the analytical continuation was done. But I could be very confident saying, okay, that even in that case, you wouldn't see it.
You wouldn't see what?
The ETH behavior.
You think that if you won't see black hole formation when you hit the Lorentzian theory with the energy of order n?
Yeah.
That would go against all intuition about gravity. It would mean that this theory wasn't really gravity. I doubt it.
But okay, these are just some
Okay. Yeah.
speculations.
Yeah.
of course.
Sorry, but let me get back to my original question.
So,
my question
if you
was,
quantize
you
the
quantize-
Schwarzian alone, can you make sense of this as?
is there a distinguished part of the Hilbert? Is there something, you know,
Mhm.
well, the Schwarzian seems so important for some things.
Yes. Yes.
On the other hand, firstly, should one be quantizing the Schwarzian? Is that the wrong thing to do? Is there any sense in which that's the right thing to do?
Mhm.
Have you seen this paper by Kitaev and Su?
No, I haven't studied it in detail, but I know about the paper. But so that I don't think I have a good answer to that. So that's why I was attempting this other answer. It seems like if this is the case, Schwarzian is not good for everything, and therefore quantizing it. That's why my intuition could be that, but I cannot.
Let me say
cannot.
again that this is exactly the kind of thing for which the Schwarzian should be good, because
Yeah, that's why we we did a calculation. Of course, I share absolutely your intuition.
okay,
I share
I
it.
would be very surprised. To me,
I
if
share
you show me that in Lorentzian space it
I
doesn't
would.
work,
Oh,
then I
sure,
would say
sure.
this theory is not a theory of gravity,
Mhm.
because it doesn't share an elementary feature of all real theories of gravity.
Yeah.
So that I would say that
But
would be reason
yes,
to
yeah.
be less interested in this thing.
Yeah.
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 But I think even if it does work,
Mhm.
there is a more sophisticated question,
Yes, there I agree.
which is about quantizing the Schwarzian.
The Schwarzian.
And you know what it means.
Yes, yes. No, I don't have a good answer for that.
Okay.
Yes.
Thank you. Other.
Well, thank you. Thank you. It was
Thank you.